Welcome to Elementary Calculus, Chapter 2, Section 5, where we're going to talk about logarithmic functions. And the first thing we need to do is have a look at what is a logarithmic function. In this box right here is a very important conversion that we need to know how to make, and that's converting from a logarithmic equation to an exponential equation, and vice versa. So being able to move back and forth between these two different formats is important. And it's also important to note that the base of a logarithmic statement, which is represented by lowercase a here in the middle of your screen, has to be greater than or equal to 0. And it's not going to be the number 1. That would be uneventful. And our x value is going to be greater than 0. And certainly, if you're working with a positive number that's being raised to a power, you're going to end up with a non-negative number, so that makes sense that our x value is going to be greater than 0. And let's do a little practice converting back and forth. 5 to the third power is certainly 125, but how do we take this exponential statement and write it in logarithmic form? What I like to do is, at the top of your screen it says y equals log base x, and if we convert that over to an exponential statement, we see that the base of, look at the location of these different values. The a is the number that ends up being raised to a power. The power is this y value that's on the other side of the equation, and x, which is part of the logarithmic statement, is really the answer. Interesting. So let's see if we can mimic that here. So this statement is really in this exponential format. Let's see what we can do. Y equals log base a of x. And my exponent is the number that's over here on the right-hand side, so that's a 3. And a is the value that's being raised to a power, that's the 5. And the answer is written full-sized here, and that's the 125. So this is your final answer. This is the exponential statement written in logarithmic form. Very often you'll see this written sort of flip-flopped, and you'll see it written as log base 5 of 125 equals 3. I prefer to write it in this second format. It's the one that I'm most used to. So even if I saw the statement written this first way, I would tend to rewrite it this way. Just for consistency's sake, it increases my chances of getting the right answer, because when I see it written this way, in my head, I read it as 5 to the power of 3 equals 125. And that's just the picture that I have in my head, so I do it that way every time. So standardize a process for yourself that's going to increase your likelihood of getting these correct. Here you see that the equation is written using my favorite format, and so I know that I'm going to be taking 2 and raising it to the power of 5, and that's going to equal 32. So when we write this in exponential form, we get exactly that. 2 to the power of 5 equals 32. And you might see some homework problems where you have to toggle back and forth between these two formats. Being familiar with that format allows us to answer this next question, where we have to evaluate this logarithm. And this is interesting because it's not already an equation, but I want to know what it equals, and you could set it equal to x or question mark or whatever you want. The sun is now blazing in through the window, and you can see the blinds are leaving me in shadow here. I'll fix that. I have no idea what x is as I'm looking at this, so it helps me to rewrite this in exponential format. I write it as 5 to the x equals 1 over 25. I'm still a little bit unsure, So I might then take it and rewrite it as 5 to the x equals 5 to the negative second power. The negative in the exponent tells me to take the reciprocal. The squaring will square the expression and give me 1 over 5 squared, which is 1 over 25. And now that I have the same base on each side of the equation, I can equate the exponents, and I get an x value of negative 2. This problem didn't say solve for x, it said figure out what this equals. I said it equals x, and now I know what x is, so my final answer is negative 2. Hopefully making that conversion into an exponential format is helpful to you. There's a lot of information on this page. Normally we don't like to read this stuff, but I'm telling you, this is good stuff. Every logarithmic function is the inverse of an exponential function. That's great, and you have gone through the process of being given a function and having to solve or create its inverse, and creating its inverse means swapping the variables and solving for that original variable. And that's basically, if not exactly, what's happening here. X is the argument here, and x is all alone on the one side of the equation here. So those are inverse functions. You know that the graph of inverse functions are mirror images of one another over the line y equals x. So that's what's being said in this statement here. And a caution, this is good, just a good reminder, the domain of a logarithmic statement, the x values that are going in there, those x values have to be greater than 0. So you can't take the log of 0 nor the log of a negative number, which opens up the door for us to need to find the domain of a logarithmic statement or logarithmic function. Remember that if there's a log and it doesn't have a base written there, then we assume it's a base of 10. If it says ln for natural log, we know that that's a base of e. Regardless of whether it's log or natural log, base 10, base e, or any other base, this argument right here, in this case x minus 4, must be strictly greater than 0. Again, I don't care what this expression is. If it's inside my log, it has to be greater than 0. I don't care what the base is, base 10, base e. The argument's got to be greater than 0. So, very simple to solve this one. Add 4 to both sides, and we find that we can only use x values that are greater than 4. Whether you express your final answer like that, or in interval notation, or on a number line, if I have 4 here, all the x values that are greater than 4 will be to the right of the number 4 with an arrow going all the way out to infinity. It's a strict inequality. The x values have to be strictly greater than 4, so we would put a parenthesis here. That would be your answer using a number line, and translating that into interval notation is nice. We use that same parenthesis, we put the 4 there, reading our shaded region from left to right. The shading goes all the way up to positive infinity, and infinity always takes a parenthesis. So there's your final answer in 3 different formats. The first format, if you want to write it in set builder notation, we have the set of x values such that x is greater than 4, and then close your set braces. That's set builder notation. We've seen so many domain problems. We know that we can't divide by 0, so if there's a fraction, a rational function, the denominator can't equal 0. If it's a radical function, if we have a square root and the variable's under the square root symbol, the radicand, the stuff under the square root symbol, must be greater than or equal to 0. And now we've got logarithmic statements where the argument must be strictly greater than 0, not greater than or equal to. Here's a set of rules that you need to refamiliarize yourself with. Some of these are rules, some of them are properties. Some of them are just unique things that happen. This is the product rule. This is the quotient rule. And this is the power rule. You definitely want to be familiar with those for the purposes of manipulating logarithmic statements and equations. This one's part D is sort of a duh, because you know now how to convert this into an exponential statement. And as an exponential statement, this would say that a to the power of 1 is equal to a. And then you say, duh. But that's a property that we might see, and it might be useful. This one is very similar. A to the power of 0 equals 1. Anything other than 0 to the power of 0 is equal to 1. So that's not a big surprise. And this one's even better, although it comes in handy. This, when we convert it to an exponential statement, says that a to the power of r, that's this a to the power of r, equals, no way, a to the r. Every once in a while, that'll help to get us out of a jam, though, so keep that in mind, and definitely keep these in mind. I'm expecting a visitor, so I'm keeping an eye out. No one exciting, just an electrician, but gotta keep an eye out. Okay, so in example number 3, we want to rewrite the expression as a sum, difference, or product. And we're going to use the properties of logarithms that we just saw on the previous page. And in this first example, log base 4 of 8 plus log base 4 of x is actually our final answer. We can't simplify either of those components, but what I used was the product rule in reverse. So let's just go up and glance again at the product rule. We have in our current problem this product of x and y that's happening in here. So the x value is the 8 and the y value is the x. That's a little confusing, but the point is that because they're connected by multiplication, they're 8 times x, we get to break them up using addition, and each one of those factors in there, the 8 and the x, in this case the x and the y, each one of them gets their own logarithm with the same base that we started with, which in our current problem is a base of 4. Now the quotient rule, which is going to be applied in our next problem, I can tell it's a quotient rule because here we have division. The result of division is called a quotient. And the part of this fraction, the numerator, is going to get its own logarithm. And the denominator also gets its own logarithm, except the two are separated by a minus sign. And I like to think of the minus sign as being this division symbol. Look how similar they look. And we'll see some more complicated versions of that. But when we break this one down, or expand this logarithm, we've got the log base 4 of the square root of 3, this time minus the log base 4 of 5. Now what I'm going to do is I'm going to modify this problem a little bit. I'd like to scribble out the 5 here, and let's change it to a 16. That means that we're going to get rid of this 5 and change it to a 16. This is a worthwhile problem to write down as a separate problem, because while this statement is equal to the next statement, we can take this one a little bit further. The log base 4 of the square root of 3. Now look at this. 4 to what power equals the square root of 3? I have no idea. However, if we look at the next term, the log, or rather 4 to what power equals 16? And the answer to that is definitely 2. So a correct final answer to this question, this modified version of the question, is what I've written a box around here. Log base 4 rad 3 minus 2. This would constitute simplifying your final answer as much as possible. All right. Now we've got log base b of a equals 3, base b of b equals negative 2. We want to use the properties of logarithms to find the value of this. I'm going to take this original statement, log base lowercase b of the product, capitals A and B. It's a product, A times B, so I'm going to use the reverse product rule. I'm going to decompose this and write it as log base b of A plus log base b of B. Log base b of A is equal to 3. Log base b of B is equal to -2. So these, instead of the equal sign there, let's put it here. This is a 3. Here's a plus. This evaluates to -2. And we're stuck with arithmetic, which we can handle. Even I can do that in my head, and I get a final answer of 1. So just different ways of compelling you to use the properties of logarithms. That's product rule and quotient rule. We didn't use the power rule yet, but it's coming. The base 10 and logarithms based E are called natural logs. That's good. I like this actually. Those are equivalent. The natural log and log base E are absolutely equivalent. Using the ln for natural log is just shorthand for log base E. Your calculator only includes the log button, which is a presumed base of 10, and the natural log button, which is a presumed or assumed base of E. If you're working on a problem that has a base of anything else, we're going to need a workaround. And that is what we're going to talk about next. It's called the change of base theorem. And you can see in the next example, in number 4, we've got a log of base 5. So we will see how to tackle that right now. So here in example 4, we're going to use the change of base property or theorem in order to evaluate this logarithm. And this is, I think every one of these problems I've seen ends up being calculator work, but we're going to set it up with paper and pencil. Notice here in the theorem, the a is the base on the original logarithm, and the x is the argument. So a is the base, x is the argument, and here we're seeing a as the argument and x as the argument, and there's a new base, b. Where did that come from? And wherever it came from, what is it supposed to be? It's going to be whatever you need it to be, as long as a isn't 1 and b isn't 1, and x is a positive number. I think maybe the best illustration is here. Base b, as I circled in the theorem at the top of the screen, it could be base 10 or it could be base e. Those are the two sort of go-to bases, because I'm going to use natural log, which is a base of e. I'm going to rewrite this expression as the natural log of 0.671 over the natural log of 5. How does that help me? I don't know what either one of those natural logs evaluate to. I don't have to. This I can plug into my calculator. My calculator has a natural log button, but it does not have a log base 5 button. I could also write this as log, which has the implied base of 10, 0.671 over the log of 5. Type either one of these fractions into your calculator and you're going to get the right answer. And we are being asked to give our answer to the nearest thousandth. So I've already shown you how to plug these into your respective calculators. I'm just going to type it into my graphing calculator. I've got the natural log of 0.671 divided by the natural log of 5. And I got negative 0.2479. That should be negative 0.247 9. So that's the change of base theorem, which allows us to use a calculator to evaluate a logarithm with any base. And then we run into logarithmic equations. No surprise, these are equations that involve logarithms, and often we're going to have to use some of the properties that we've already explored in order to solve these statements. For example, on the left-hand side of example number 5, I have a logarithm or a pair of logs that are separated by a minus sign, so I'm going to use the reverse quotient rule to rewrite that as the log with an implied base of 10. And for some reason my pen's not writing anymore. Come on now. My tablet has frozen. So I'm going to pause and I'll be right back. Alright, after what seems to have been simply a dead battery in my Apple Pencil, I charged it a little bit and let's see if we are back up and running. Looks like it. We'll see how long it holds out. I've been using this thing like crazy lately. So we were about to use the reverse quotient rule on the left-hand side of this equation. We've got log with implied base of 10. Since it's a subtraction problem, that's how I knew it was the reverse quotient rule. With a positive leading coefficient here of positive 1, which is invisible, we know that the 2 plus x goes into the numerator. This negative coefficient here tells me that the x minus 3 goes into the denominator. And the right-hand side is still log of 2. Now that our logs on both sides of the equation have the same base, we've got a log of capital A equals a log of capital B. That means we can set A equal to B and finish solving this problem. I'm going to move over to the left a little bit to make sure I have enough room to finish working this out. So let's set 2 plus x over x minus 3 equal to 2. Then I'll multiply both sides by x minus 3, giving us 2 plus x equals 2 times the quantity x minus 3. This is very straightforward stuff, right? We've gotten to the point in the problem where we know what we're doing. I know how to do this. That's great. Again, what that means is that the thing that you need to focus on is getting from here, or really the initial problem, to this first step and then to this second step, and from there you know that you can handle it. So during your review process, make sure that you're reminding yourself or studying the fact that a logarithmic equation needs to be balanced out or manipulated so that you have two logs equal to each other with a common base so that you can set their arguments equal to each other, and from there hopefully it's a piece of cake. Let's finish solving this. Distributing the multiplication by 2 on the right hand side, we've got 2 plus x equals 2x minus 6. Subtract x from both sides. Add 6 to both sides. And we've got an answer of 8. Is it worth taking this and plugging it back into the original question? It's not going to hurt, except for the fact that I don't know what the log of 10 is, nor do I know what the log of 5 is, but I do know that 10 divided by 5 is equal to 2, which is what this says, which means I think we're in good shape. If if this process over here had resulted in there being an x to the second power, for example, then we have to square root both sides of our equation at some point, which ends up giving us a plus or minus value. Those two values, with two values, it would definitely be worth doing a quick check to make sure that both of those values plug back into the equation and give us a true statement. Make sure that both of those potential solutions satisfy the original equation. But in this case, I'm going to go ahead and put a box around my x value of 8. And let's move into the next problem. Both sides of the equation only contain one log. They both have a common base of 10, which means I can set the arguments equal to each other. Subtract x from both sides. Subtract 1 from both sides. And yet again, this looks like a good solution. It's too easy. I'm looking through it and double checking to make sure I didn't make a mistake, because this just seems too straightforward. I'm going to subtract x and subtract 1 and 3. The x, good. And let's do a quick check. We've got time. This turns out to be 7. 3 times 2 is 6, plus 1 makes 7. Looks good. X equals 3 is our solution. And then we come back to a quick revisiting of exponential equations. We're coming back and looking at these because we've been working with logarithms and logarithms and logarithms, and even though this question at a glance might not look like a logarithmic equation, we do indeed need to utilize logarithms. It doesn't matter whether you take the log or the natural log of both sides. I'm going to take the natural log. It doesn't matter whether I take the log or the natural log, although I would use one of those too, because either one of those allows us to use the power rule for logs, which says that we can take this exponent and bring it out front of the logarithm like it's a coefficient. So let's do that. Applying the power rule, we write this as x times the natural log of 3 equals the natural log of 17. We can then divide both sides by the natural log of 3 to find that x is equal to the natural log of 17 over the natural log of 3. We've talked about how to type this into a calculator already. If the question that you were presented with gave more specific instructions on how to present your final answer, you might have to give an exact answer, which means you would answer with natural log 17 over natural log 3. In the case of a decimal approximation, I will drum up a quick numerical value for you. Natural log 17. I'm on my graphing calculator. I typed in natural log 17. I made sure to close the parentheses. I've got all the reflections now. I made sure to close the parentheses after the 17 because I'm about to type in divided by the natural log of 3, and I want to make sure that the 17 stays contained in that initial natural log. I don't want to divide the 17 by the natural log of 3. So divided by natural log 3, enter. So if you're on a grapher, this is what your input should look like. If you're on a 2-line entry scientific calculator, this is also what your input should look like. Natural log 17 divided by natural log 3, I got 2.5789. That's rounded to 4 decimal places. Let's get that decimal point a little bigger. There we go. And that takes us into our next problem, which is an application problem. And our last problem of the section. The purchasing power of $1 is decreasing at a rate of 3% annually, compounded continuously. How long will it take for the purchasing power of $1 to be worth 67 cents? How long? I'm going to assume that we're measuring in years, and I'm going to, because we're compounding continuously, I know that I need to use the Pert formula, so I will jot that down. Final amount equals starting amount times e to the rate times time. My starting amount is $1. You can write just the number 1 or 1.00. Our final amount should be 0.67. E is a number. Our rate, this is interesting, the rate is 3%, but it's a rate of decrease. So I'm going to make my R value negative 0.03. And we're trying to figure out how much time that's going to take for the value of the dollar to change. So I don't know my t value yet. Now multiplication by 1 right here isn't doing anything. So I'm going to disregard that. And I'm going to rewrite this exponent without the parentheses. I just did that to sort of encapsulate the rate of negative 0.03. So let's rewrite this as 0.67 equals e to the negative 0.03 t. This problem is extremely similar to this problem. Our variable is in the exponent position, so we have a number to a variable power equals a number. And here we have a number is equal to a number, e, in this case, being raised to a variable power. Yes, the exponent has an additional multiple in it, but we're going to use the same technique. I'm still going to take the natural log of both sides. So we have the natural log of 0.67. That was a z. There we go, 67 equals the natural log of e to the negative 0.03 t. All right, how does that help me again? Well, I can use the reverse power rule. I can take that exponent and bring it out front of the natural log like it's a coefficient. So let's make that move. Natural log 0.67 equals negative 0.03 t times the natural log of e. So nice that we're able to take the entire exponent and bring it out front. The natural log of e can be evaluated. You could type it into your calculator, although it would be a little bit cumbersome to type it in. But remember that natural log is the same thing as log, well, I don't want to write it like that. Let's do this. Let's put a little note that the natural log of e is the same thing as the log base e of e. And log base e of e is actually asking us a question. What this says is e to what power equals e? And the answer is 1. So the natural log of e is equal to 1. That's why some people say that the natural log and the e cancel each other out, because this is going to go away, leaving us just with the exponent. I like to say that it sort of falls down onto the ground, and it's going to be there all on its own, which is great. Now we've got direct access to the variable. We'll get rid of the highlighting there, although you could insert some of that if you wanted to. So the natural log of e is equal to 1. You could write that in if it'll fit, equals 1. Yep, that made it. And we can keep going with this. So the natural log of 0.67 equals negative 0.03 t. Divide both sides by negative 0.03 in order to isolate our t value on the right hand side. So we have natural log of 0.67 divided by negative 0.03 is equal to t, and then we have to type this into a calculator in order to get our t value, and we'll do some rounding and we'll be done. So I'm on my grapher again and I'm typing natural log 0.67. I'm closing my parentheses after the 0.67 divided by negative 0.03 equals, and I got let's see, let's make sure we're rounding to the nearest hundredth. So rounded, I get 13.35 because I've got 13.349. So I will say 13.35 approximately equals t. If any of you don't have a lot of experience with your grapher, or if any of you type that in and you got an error, don't forget, and it works similarly on scientific calculators, the where is it? This button up here is subtraction, but this button down here is the negative sign. So when you want to type -5, you have to hit this negative button and then type 5, and that would give you, can we see it there? That'll give us the -5. It's there. If you've got this very nice calculator, hopefully you already know how to use it. And good news is that wraps up this section. So I hope very much that that was beneficial to you. A good review of compound interest and continuous interest, and we got to see a lot of the properties of logarithms. We saw the big three properties: product rule, quotient rule, power rule. Please make sure that you are well versed in those. And actually, this statement right here, I think that was the last statement in that table of properties, so to speak, that we saw that had the log base a of a, I think it was. So when the base and the argument are the same, that logarithm is going to evaluate to 1. All right, on to the next section. See you there.